All right, so the objective of the lab on this side of the room today is going to be Archimedes' principle. So the story behind Archimedes is that the king came to him and asked him, hey, somebody made me a crown full of gold. I want to make sure it's actual gold. The story's something like that. I don't know if that's the actual story. It's so old, so long since I've actually gone through it. But feel free to write it up in your background. I won't read it. But the objective of this experiment is you're going to find the density of 3 different objects on your table in 2 different ways. So one of the ways is going to be using Archimedes' principle, and another way is going to be using the old-fashioned chemistry formula that you probably learned at some point, where you just take mass and divide it by volume. So I'll walk you through the procedure real quick. And so basically you have a scale. First step is you take your scale down from its perch, place it down on the table, find the mass of one of your objects on the table. Once you have the mass of the object on the table, okay, the next step is you want to go ahead and suspend the scale back up on the perch, like so, and then find the mass a second time, all right? Make sure these 2 values agree. One of the things that happens is when this scale gets put up on this perch, it is a triple beam balance. So if it is not level, then it'll look like it's not pointing at the proper value. Of course, I don't have it pointing there now. But, if it is not balanced, rather than sit there and toy with it trying to get it balanced, what I do is I take a piece of tape and I mark off where level is. Okay, so you might find that this thing is offset a little bit, all right? And that's why I say find out what the mass is on the table, then put it up on the perch and find the mass that way. That way you know what it should be, and that way you can level the scale properly. And the next step is, once you find the mass, record it as m air, all right, as the mass in air, and then use your rubber band, tie up the object, and you're going to suspend it in water. Now, when you suspend this in water, you'll get a buoyant force on the object, which will cause an upward force. It'll appear that the mass decreases, all right, so you'll see the mass of the object goes down. However, as a theorist, I would be wrong if I didn't tell you, please do not write that the mass decreases, because the mass of an object does not decrease. It's an intrinsic property of an object. What's actually happening is the weight is decreasing. So even though this balance finds a mass, okay, it's really taking a force and it's dividing by 9.8 to get the mass, all right? When you step on a scale and you get pounds, pounds is a unit of force. Pounds is not analogous to mass, all right? The reason that you have a scale here and you get mass is because this actually divides by 9.8 for you. So, long story short, the mass will go down. You'll write that as the mass submerged, which will be this value, and it'll be less than this value. So then you'll plug into this equation, and you'll calculate it using the density of the fluid. This part's really easy, even though I made it look hard. The density of fluid is 1 gram per cubic centimeter. That's the density of water. All right. Just a heads up, you may think it's a potential source for error because, what if the density of water is not? We were just given this value. You can test it. You grab a certain amount of water, you have a given volume of water, take the mass of that water, and you divide it by the volume, you'll get the density. Spoiler alert, it's probably close to 1. Okay, so you'll get the density one way using this formula, then you'll get the density the second way using the value that you already found for mass and air, and you'll divide it by the volume of the object. So there's 2 simple kinds of objects. There's either a cube or there's a cylinder. You can take the formulas. The volume of a cube is side cubed. However, some of these cubes, just double check, because some of these cubes are not perfect cubes. So maybe check a few of the sides to make sure that all sides are equal. If they're not, then multiply side by side by side with whatever measurements you take. Okay, that's how you find the volume for a cube. Find the volume for a cylinder. Measure the diameter of the cylinder and divide that by 2 to get the radius of the cylinder. And then plug into this equation. So pi times the radius squared times the length of the cylinder, and that'll give you the volume of the cylinder. Then you plug into this equation and you obtain density the second way. And then you can do a comparison. Now in this case, this is percent difference. So for those of you who've been writing in your lab reports, percent difference and percent error. Percent error is when we're using it compared to a relatively accepted value, a known value. Percent difference is when we obtain the value 2 different ways, okay? So if I obtain the values, or I have to obtain the values in these equations using measured values, all right, in both cases. So neither one of these are the actual accepted measurements, all right? So You'll do a percent difference, then you'll move on to the next one. And your bonus question, I haven't written it down yet, but it's going to be, how would this experiment change if I increase the temperature in the room? Okay? How would this experiment change, and how would your punctuality change if I gave you coffee? Show up on time? Probably. Anyway, so that's that experiment. This experiment, rotational motion. So there's going to be 2 different radius that I'm going to have you choose, okay? And that's the key to this experiment. The radial values. So the radial values are marked out on your apparatus. So these numbers on the bottom are the radial values in centimeters, okay? That tells you the distance from this to the center of rotation of this object, all right? The spring is disconnected, but I'm going to connect it because it's going to need to be connected. All right, so here's a hint, okay? And heed this hint because it's very important. Choose 2 radial values that are relatively small. Don't choose these outer ones because what's going to happen is you're going to really need to cook this thing around, and it becomes more and more difficult to actually do the timing for this the further radius you choose. So I would choose, like, 14 and 17 or 15 and 16, whatever you want. All right, the first step is you're going to measure the mass of the bob and write that down. All right, this is the bob by itself, and that's why it was disconnected. So find the mass of that on a triple beam balance. You might have to wander over to the, are there any loose ones on this side? One in the back, really? I want to borrow someone else's. There's one over here. Okay, yeah. So find yourself a triple beam balance. I don't know why they're going so scarce. All right. All right, so the next step you want to do is measure the height of the tape. And just go a little bit higher. All right. So the important thing is when you're measuring this piece of paper and when you're lining it up, line up the tape, line up the piece of paper so it only flicks the tip. All right, you don't want it flicking other parts of the cone. So I only have the very tip of this cone flicking the piece of paper as it passes by. That is important for getting accurate measurements. The other thing you have to make sure is that the spring is keeping you inside, all right? Because the idea behind this is I'm going to start to spin this, and when I do spin it, it's going to create a centripetal acceleration, which is inward, all right? It's going to cause a centrifugal acceleration, a fictitious force, which pulls it outward, all right? And it causes the bob to move out from center, just like you would if you spun a ball on a rope, okay? So I'll start to spin it, and let's see if this works today. It does. This didn't work either. All right, so I'll start to spin it, and what we're going to do is we're going to listen for the flicks. You can hear the flicks. I'm going to get it outside of that radius, so I'm going to spin it a little faster, and I'm going to let it degrade, and then I'm going to time it. Okay? The important thing is, in this lab, and the thing that almost every class that I've taught, at least one group gets wrong, is counting to 5, all right? And the reason why is because when you hear a flick, you start the timer, you start it on a flick, you do not count 1 the minute you start a timer, okay? You count 1 on the next consecutive flick, okay? And that's 1 revolution, all right? So a lot of times when people get 20–30% errors, it's because you're counting 4 revolutions and not 5 revolutions. And it's a very simple thing. So you start spinning it, you hear a flick, you try to time it, tempo, start on a flick, count 1 the next flick, and stop on the 5th one. All right, so counting 5 revolutions. Do that at least 2 to 3 times, all right, to make sure that you're getting consistent values for the period measurement, or for the total time. And then what you do is you take this total time and you divide it by 5 to get the period of revolution, which is tau. Then you can figure out the angular frequency by taking 2 pi and dividing it by tau, so you get omega. And then you can figure out the centripetal acceleration by taking the radius and multiplying it by omega squared. All right, so that's one value you need is the centripetal acceleration. I'm going to give you a heads up. You do need to convert this to meters, and the reason why is because you'll be using gravity in the second equation. All right, and that's meters per second squared. So you will need that to cancel out properly. Convert that radius into meters. The next step is to find the applied force that you need to get out to that radius. So what I'll do is then I'll suspend a mass in a hanger over the edge like so. And I will add mass and continue to add mass until I reach a point where I'm at the given radius that I measured for those oscillations, okay? So you'll add more and more mass. Whatever mass you add, remember to count the hanger because it's 50 grams. Whatever mass you add, you want to multiply that by gravity. You don't have to change the mass from grams, so you can measure in grams. If you measure the mass of the bob in grams, because you're just going to get your answer back in grams, okay? So whatever applied force you find, which is just the mass you put on the hanger times gravity, you take that value and divide your previous value, the centripetal acceleration. You divide those two values and you should find that the answer you get is the mass of the bob, okay? You do that compared to the measured mass of the bob using the scale, triple mean balance, and you get a percent error, okay? So, you'll do that, and you'll do that for one radius, and the percent error should be less than 10. And then do it for the second radius. And what you'll find is obviously a different omega, but you'll also find a different applied force. So you should still get the mass of the bob regardless. All right, and your bonus question for this lab is going to be, how would this experiment change if I were to put it at the center of a merry-go-round? All right, and here's my hint to you guys. So if I were to put this at the very dead center of a merry-go-round, and I were to spin the merry-go-round, how would this experiment change? Okay, that's the only hint I'm going to give you. Feel free to use a rolly chair like they did one semester to try to figure it out. Or you can ask me questions. Guys, remember my bonus questions, you can always ask me questions. All right, I may not necessarily answer them, but I'll try to point you in the right direction.